Good morning, dear students. Already you got a discussion with the Wheatstone's network. Now we are going to speak about meter bridge. Before discussing meter bridge, we have to recall some of the fundamentals in Wheatstone's network. As you know, in the previous discussion, you got an expression P by Q is equal to R divided by S, which is the condition for bridge balance. If the bridge is said to be under balance, if all the four resistances in the four arms of the Wheatstone network are said to be in a balanced condition, then you will get an expression P by Q equals R by S. Or if this condition is satisfied, then you can say the bridge is said to be balanced. In a balanced condition, no current will flow through the galvanometer, as you know. No current will flow through the galvanometer. The current Ig through the galvanometer is 0. Then the potential at this point B and the potential at this point D are same. Potential Vb is equal to Vd. This condition will be satisfied in a Wheatstone network. Then PQ, RS, this P by Q and R by S are said to be in the balanced condition. Now, if the galvanometer and the battery and the key are interchanged across the ends, then what will happen? If suppose instead of connecting the galvanometer across B and D, I am shifting this galvanometer to this between these 2 points A and C, and then the Lagrange cell and key are taken between B and D, then what will happen? Once again the bridge is said to be under balance. Once again the bridge is said to be under balance. How? We can check here. If the galvanometer is taken between A and C and the Lagrange cell is taken between B and D, then the circuit will be like this. Actually, I have taken the battery and the key between B and D, and between A and C have shifted this galvanometer. Then once again what will happen? This is P, this is Q, and this one is R and this one is S. Then you have to take the junctions which are holding the galvanometer. Now A and C are holding the galvanometer. Then I can write R by P equals S divided by Q. R by P equals S divided by Q. If suppose I am having resistance value 2 ohm, 4 ohm, 4 ohm and 8 ohm like this, then the bridge is said to be under balance 2 by 4 and 4 by 8, 1 by 2, 1 by 2. In the same way, if you write the condition for the same resistances, R is 4 ohm, P is 2 ohm, Q is 4 ohm, S is 8 ohm. Then as per this condition, R is 4 ohm, P is 2 ohm, S is 8 ohm, Q is 4 ohm. Once again we can say the bridge is said to be under balance. So if the galvanometer and the cell across the terminals are interchanged, once again the bridge is said to be under balanced. Condition is that earlier the bridge must be balanced. Then after interchanging the galvanometer and Lagrange cell, once again the bridge is said to be under balance. And we can say here, if you check out the entire Wheatstone network, we can check out how many number of closed paths or closed circuits can be taken here. Here we can have 7 closed circuits. 7 closed circuits. If you look at the case here, this is a closed loop. We can say A, B, D, A, and another one A, B, C, D, A, and another one A, B, D, C, and then A, and another one A, D, B, C, and then A. Then A, B, C, A, D, C, A. If you count all these closed circuits, then you will get 7 closed circuits. This is also an important question which will be asked in Wheatstone's network, right? Now, as per fundamentals of Wheatstone network, we need 4 arms which possess 4 resistances, then a galvanometer, then a Lagrange cell and a key. We are going to modify this Wheatstone network, and we are going to speak about a measuring device called meter bridge, which is used to determine the values of unknown resistances, also the specific resistances. Meter bridge. Meter bridge is another form of Wheatstone's bridge. There is another form of Wheatstone's bridge. It consists of 1 meter long manganese wire, which is stretched along with a wooden scale, and it is fixed on a wooden board between two copper strips C and D. Between two copper strips C and D. Meter bridge is another form of Wheatstone's bridge. It consists of 1 meter long wire, manganese wire especially, which is stretched along with a wooden scale, is fixed over a wooden board between two copper strips C and D. Let me show you the meter bridge apparatus. This is the one. This is the meter bridge apparatus. It consists of a manganese wire. This is the manganese wire, which is 1 meter long, which is stretched along with a wooden scale, fixed on a wooden board. This is the wooden board between two copper strips. This is the copper strip C, and this is the copper strip D. So the ends of the copper strips are connected with the manganese wire. Can show it with the diagram also. This is the wooden board. C and D are the two copper strips. This is C, and this one is D. These are the two copper strips. A manganese wire is fixed over CD along with the meter scale, which is 1 meter long. Another copper strip, let us say E, is fixed between the two copper strips C and D. Between two copper strips C and D. You can see another copper strip E is fixed between the C and D to enclose the gaps G1 and G2. So two gaps are generated. We can call the gaps as G1 and G2. E is the metal strip, copper strip, which is fixed between the two copper strips C and D to enclose the gaps G1 and G2. So E is the metal strip here. Now, the copper strip has a terminal E over here, which is connected to a jockey through a galvanometer and a high resistance HR. This is nothing but a conducting wire. Jockey is nothing but a conducting wire, which is connected to the terminal E, middle terminal E, through a galvanometer and a high resistance. I can show you the jockey and the high resistance, even a galvanometer. This one is jockey, which is nothing but a metal rod. This is the insulating protection here. This is a jockey, and this is a high resistance. This one is the high resistance, and this one is the galvanometer. All these things are connected in a series. Jockey is connected to the terminal E through a galvanometer and high resistance. Which one should come after jockey? High resistance, because this high resistance will protect the galvanometer from the damaging effects if large current flows through the circuit. Now, the gaps G1 and G2 are generated. Across the gap G1, we are going to connect an unknown resistance, let us say P. P is unknown. A known resistance P is connected across the gap G1, and the known resistance or a standard resistance Q is connected across the gap G2. So across the gap G1, you are connecting unknown resistance, which is P. Across the gap G2, you are connecting a known resistance, which is Q. To the terminal E, you are connecting the jockey J through the galvanometer and a high resistance. galvanometer and high resistance. A standard resistance will be of this form. This is the standard resistance. We can have any value from 1 to 10. It's a multiple of 1 ohm. In the sense, if I bring the switch over here, this notch is pointing towards a 6. So this is said to have a 6 ohm resistance now. If I am keeping this over here, 3 ohm resistance, and then this is giving you 1 ohm resistance. So depending upon the position of the notch over this knob, we can have any value of resistance, standard resistance. This is a standard resistance. Unknown resistance can be any wire, any material wire. I'm just showing you a wire here. Material wire will be given. That is the experimental wire whose resistance has to be determined. Also, whose specific resistance must be determined. I'm showing you a copper wire here. This material wire whose resistance has to be determined with the help of a meter bridge circuit. Fine. So across the gap G1, you are connecting an unknown resistance P. Across the gap G2, you are connecting a known resistance Q. From the terminal E, you are connecting a jockey through a galvanometer and a high resistance. Between the terminals A and B, you are connecting a Lagrange cell and a key. Between A and B, you are connecting a Lagrange cell and a key. Key is this one. Key is this one. This is the key. It's like a C and D, which is connected by a metal strip or a metal rod. So this acts as a key which will permit the current to flow through the circuit, or which will disable the current to flow through the circuit. So this is the entire circuit of a meter bridge circuit. So another form of Wheatstone's bridge. It consists of a manganese wire. What is the purpose of selecting a manganese wire as a meter bridge wire? Why shall not we select a copper wire as a meter bridge wire? A meter bridge wire should possess high specific resistance and a low temperature coefficient of resistance. What is temperature coefficient of resistance? As you know, as the temperature increases, the resistance of the material wire will also vary. If any material shows very low change in its resistance value with increase in temperature, then that material is said to possessing low temperature coefficient of resistance. Generally, alloys have that characteristics. You might have seen with this graph, rho versus temperature. The variation of specific resistance with respect to temperature is less here. This is for alloys. Whereas in the case of metals, we can say the specific resistance increases with the increase in temperature. So alloy shows a very low temperature coefficient of resistance, so it is selected as the meter bridge wire. Whereas copper wire has low specific resistance and high temperature coefficient of resistance, which means as the temperature increases, the resistance of copper wire will also increase rapidly because it is a metal. So copper wire is not suitable for meter bridge wire. Only alloys like manganese, constant, they are all possessing this high specific resistance and low temperature coefficient of resistance, so you can use it as meter bridge wire. Now we shall see how to determine the value of the unknown resistance P. Now, the jockey must be moved over the meter bridge wire. At one particular point, the galvanometer will show zero deflection. In a Wheatstone network, you have seen the galvanometer will show zero deflection when the bridge is said to be balanced. If bridge is said to be balanced, then we have to say the resistance ratio must be equal. The resistance values in the four arms must balance each other. In the sense, P by Q must be equal to R by S. We have the resistances P and Q, no problem. Where is R and S? Now we can say that this length of the meter bridge wire between AJ and JB now replaces the resistances R and S, because they have certain amount of resistance. If R prime is supposed to be the resistance per unit length of the meter bridge wire, then if this resistance R prime multiplied with AJ will give you the value of resistance, let us say R, and then this JB will give you the value of the other resistance S. So it all depends upon the values of P and Q connected across the gaps G1 and G2. If the value of P is more, then the corresponding length of AJ will be more. If P is less, AJ will be less. Once again, I would like to explain it clearly that if R prime is the resistance per unit length of the meter bridge wire, R prime is the resistance per unit length of the meter bridge wire, which means it is the resistance for 1 meter length. If resistance for 1 meter length is R prime, what will be the resistance for 2 meter length? 2 into R prime. 3 meter length, 3 into R prime. Half meter length, 0.5 into R prime. For AJ length, it is AJ into R prime. So AJ into R prime now replaces the resistance R, and JB into R prime will replace the resistance, let us say S. If I take this AJ as length L1, and JC as or JB as length L2, then we can say here the resistance R value is equal to the length L1 and S value is equal to length L2, which is 100 minus of L1, because this meter bridge wire is said to have 1 meter length, which is equivalent to 100 centimeter. So 100 minus of L1 will give you the length of this meter bridge wire JB. Now, as per the balance condition, we can write P by Q is equal to R by S, which is equal to R prime into AJ divided by R prime into JB, which is equal to L1 divided by L2. Why I am bringing this condition P by Q equals R by S? We can say here, as the jockey is moved over the meter bridge wire, at one particular point the galvanometer shows zero deflection. If the galvanometer shows zero deflection, these 2 points E and J will be at the same potential. Then what will happen? If there is the same potential existing here, then the resistance across the gap G1 and the resistance between the length AJ must be equal. Similarly, the resistance between across the gap G2 and the resistance between JB is equal. So we can say here the lengths AJ and JB now replaces the resistances R and S of the Wheatstone network. So a Wheatstone network is modified in the form of a meter bridge circuit. So P is existing as it is, Q is existing as it is. You just compare the diagram with Wheatstone network. PQ, 2 arms are there. RS, instead of R you have AJ, instead of S you have JB, and then a galvanometer is between E and J, and then a Lagrange cell and a key. The entire circuitry is over. So P by Q equals R by S, which is R prime into AJ. As I've told you earlier, R prime is the resistance per unit length of the wire. Unit length is 1 meter. For 1 meter length, the resistance is R prime. So what is the resistance for the length AJ, which is R prime into AJ? For JB, R prime into JB. R prime gets cancelled out, AJ and JB. AJ is said to have length L1 and JB is said to have length L2. So I can simply write P by Q equals L1 divided by L2. Instead of R and S, I am having L1 and L2. So if I know the lengths L1 and L2, and if the known resistance Q is there, then unknown resistance P can be easily determined. So the unknown resistance P is equal to Q into L1 divided by L2. L1 divided by L2. So if the unknown resistance has to be calculated, we need to know the values of the lengths L1 and L2. So P equals Q into L1 divided by L2. This is the one. Shall we say the value what we determined here is exact? No. There are certain reasons why the value of unknown resistance will not be exact. Simply, I can say here, this meter bridge wire is fixed across the terminals like this one. They are screwed over the wooden board. You cannot fix exactly a 1 meter long wire with a screw. You need extra length of the wire, then only you can fix it on the wooden board. One thing. Second thing, there are other ways by which we can fix the 1 meter long wire, that is by soldering across the copper strips or C and D. So during soldering also, there are possibilities to have a different value of resistance. Another value of resistance do exist. We used to call it end resistance. Simply I can say here, if 1 meter is going to be fixed over the wooden board, the extra length will have some resistance. This is not taken into account, but this should be included. Or otherwise, if this is soldered between 2 points, due to soldering effects, there will be some amount of extra resistance which will get added up. We used to call this resistance as end resistance. Due to end resistance, the value of P will not be exact. In order to bring out the nearly equal value of the unknown resistance, what we have to do is, we have to exchange or interchange the resistances across the gaps. And we have to perform the experiment once again. You have to repeat the experiment once again. How? Across the gap G1 have connected P. Across the gap G2 have connected Q. Now, the Q must be connected across G1 and the P must be connected across G2. The resistance should be interchanged across the gaps G1 and G2. And the same experiment must be performed. So, if P1 is the resistance obtained or unknown resistance obtained with the P across the left gap, now I can say P2 is equal to Q into L, I can put L3 divided by L4. Reverse, you have to measure the length in the reverse order. If I am measuring L1 and L2, then after interchanging the resistances, you have to measure L3 and L4. So that will give you the resistance P2. If you take an average, that is P equals P1 plus P2 divided by 2, you will get the value of the unknown resistance. You will get the value of the unknown resistance P. So unknown resistance can be determined. How will you determine the value of unknown resistance? We have to use a meter bridge initially with an unknown resistance across the gap G1 and unknown resistance across the gap G2. After performing the experiment, you will be getting an expression like this: P1 equals Q into L1 divided by L2. What exactly you are doing is you are simply measuring the lengths L1 and L2. Now, you are interchanging the resistances across the gaps, and then once again you are measuring the lengths L3 and L4, and then you are determining the unknown resistance P2 equals Q into L3 by L4. P1 is obtained, P2 is obtained. This 2 will give you the nearly equal value or exact value of the unknown resistance P connected across the gap G1. So, in the beginning, I told you a meter bridge serves for the purpose of determining the value of unknown resistance. Also, it is used to determine the value of specific resistance of the given material wire. As you know, the resistance of the wire R equals rho L divided by A, where rho is the specific resistance. Where rho is the specific resistance. L is the length of the given wire, experimental wire. Where L is the length of the experimental wire. A is the area of cross section of the wire. A is the area of cross section of the wire. I can show you here. This is the material wire given. This has a length L. And this has an area of cross section. This wire has an area of cross section. If you cut it, you will have area of cross section A. Then you can determine the value of specific resistance. Rho equals RA divided by L, which is R into pi R square divided by L. R into pi R square divided by L. So with the value of unknown resistance determined, what is the value of unknown resistance here? We have taken P. So P into pi R square divided by L will give you the value of the specific resistance of the given material wire. So, with the meter bridge circuit, we can determine the value of unknown resistance as well as the value of specific resistance. We shall see the example 2.25 related to meter bridge. In a meter bridge with a standard resistance of 15 ohm in the right gap, standard resistance is Q, which is 15 ohm in the right gap. The ratio of the balancing length L1 by L2 is equal to 3:2. Balancing length L1 by L2 is 3:2. Find the value of the other resistance. You are asked to calculate the value of other resistance, unknown resistance. As per the expression, P by Q is equal to L1 divided by L2. L1 divided by L2. P equals Q into L1 by L2. P equals Q is 15. L1 is 3. L2 is 2. So this is 7.5. So 22.5 ohm. What do you understand from this problem? The unknown resistance value is 22.5 ohm. You just look at the expression. The length whose ratios is given as 3:2. The balancing length AJ is 3 and the balancing length L2 is 2. Is in the ratio 3:2. So we can understand that the value of unknown resistance must be greater than the value of known resistance. Then only this ratio will be coming as 3/2. If unknown resistance is less, balancing length will be less. If unknown resistance is more, balancing length will be more. As the ratio is given 3/2, you should guess and you should understand that the unknown resistance must come as a greater magnitude when compared to the known resistance. This is example 2.25. We shall go on to the another problem, example problem 2.26. In a meter bridge, the value of the resistance in the resistance box. The resistance box here is the non-resistance. Is 10 ohm. Q is 10 ohm. The balancing length is L1 equals 55 centimeter. L1 is 55 centimeter. Find the value of unknown resistance. They are asking you to calculate the value of unknown resistance. Actually, L1 is given. We have to find out L2, which is 100 centimeter minus of L1. So 100 minus of 55 is 45 centimeter. So L2 is 45 centimeter. We know P by Q equals L1 divided by L2. L1 is 55 centimeter. L2 is 45 centimeter. So P equals Q into L1 by L2. Q is 10 multiplied by 55 divided by 45. This is 11 divided by 9. 10 into 11, 110 divided by 9. So you will have 12.2 nearly. So the value of unknown resistance is 12.2 ohm. So what you are doing is, you are given the value of L1, you are finding out the value of L2, which is 100 minus of L1. So 100 minus of 55 is 45 centimeter. After getting the value of L2, you can easily determine the value of unknown resistance P, which is 10 into 55 by 45, which is nothing but 12.2 ohm. Thank you.